Hi everyone, I'm Sara, and today I'm going to be talking to you about our efforts to close the sea level budget using satellite altimetry, GRACE, and data from Argo. The steric sea level anomalies are changes in sea level due to density changes, and there are multiple ways of estimating it. You can estimate steric sea level anomalies directly by using Argo floats, or indirectly by subtracting satellite gravity from satellite altimetry. And to close the sea level budget, you want the global average of direct measurements to equal the global average of indirect measurements. Now, people usually use gridded products of altimetry, GRACE, and Argo for similar types of work, but we're individually integrating each Argo profile instead of starting with a pre-made temperature salinity grid. So for this work, we're going to start with an initial guess of steric sea level by subtracting GRACE data from altimetry data, and then later updating that map with Argo data. So here you can see a snapshot of the raw satellite data for a single month. We then use optimal interpolation to extract the long-wave signal and reduce sampling errors due to slope features using these equations right up here. This is particularly important when we update this map using Argo because data collected by Argo floats stuck within eddies can skew our results. And here's an example of why we want to remove those small scale processes. This is an optimal interpolation of steric sea level of the full satellite data. And this is using that same mapping method using just 3,000 random observations from satellite altimetry. And you can see, here's just a couple of the differences that you can see in here. And for this reason, we're treating mesoscale features as spatially correlated errors for our calculation in order to remove this kind of variability. And this figure shows global mean sea level anomalies for the raw altimeter data, which includes all of those mesoscale features in blue and the long wave optimal interpolation in red. And as you can see, the two lines match up pretty well, so we know that using optimal interpolation is sufficient for determining global steric sea level anomalies. Now, as far as Argo goes, we're only using profiles with delayed time data and good quality control flags, and only using profiles with measurements below 1,000 meters. And in this figure here, you can see a time series of just how many Argo profiles there are that meet our criteria. So for our calculations, we first match an Argo profile location with an Argo climatology, and then we calculate the density for both the Argo and climatological values using a thermodynamic equation of seawater. And this figure right here shows the depth density profile of Argo in blue, and it's matching climatological values in black. And what we do next is take the difference between the two and vertically integrate to get total steric sea level anomalies, thermosteric sea level anomalies, which are due to temperature changes, and halosteric sea level anomalies, which are due to salinity changes. Now here you can see that same initial guess steric sea level map from a couple of slides ago. And to update that map, we subtract that satellite sea level anomaly from the just computed Argo steric sea level anomalies, and then map the residuals using that same optimal interpolation function. And it may be difficult to see at first, but there are quite a few differences throughout this updated map than from our original. Now, overall, this mapping method has been working really well, but we're still seeing this salinity bias that we know is not related to mesoscale features like eddies because we're using only the long wave signals. This figure right here shows the mean sea level from the total thermosteric sea level anomalies in red and the thermosteric sea level anomalies in blue. And global salinity variation should be really small. So these two figures, or these two lines, really should match up, and they mostly do until about 2017, where we see this deviation where thermosteric sea level anomalies are greater than total steric sea level anomalies, which suggests that the ocean is getting saltier, which doesn't quite make so much sense. So we've been investigating this issue. Overall, we've tried a handful of different ways, and we're currently looking at temperature and salinity plots for individual Argos or Argo floats. As you guys know, temperature and salinity are conservative properties. They're set at the ocean surface due to interactions with the atmosphere, and below the surface, changes really should only happen due to mixing. So we know that temperature and salinity should not really drastically change over the time period that we're looking at below the mixed layer depth. So right now we're looking at below 1,000 meters. And this is what we expect to see from these temperature salinity plots. This plot is for a single Argo float with temperature and salinity values below 1,000 meters, and it's in the North Atlantic. The colorful lines are each individual profiles from that particular Argo float, and the black lines are the matching climatological values for that float. And as you can see, they match up really nicely, which is what we like. And we have a lot of really good data. We're seeing a lot of floats with their data matching up with the climatology really nicely, both before and after 2017. But we're also seeing a lot of weird stuff. We have some that show this like salty bias, like I was talking about earlier, but then we also have some that show fresher stuff and some that show kind of both. So we're still investigating this, but we're hoping that using this method, we can identify these biased floats and remove them from our calculation for updating the map of steric sea level, so that we don't have all of this weird salty bias stuff and other biases. And then once we identify these Argo floats, we're going to be looking for commonalities amongst all of them. So whether they have the same sensor type or brand, or the same group deployed those floats, or other factors that I haven't really considered yet. Thank you.